Hello, ladies and gentlemen. We're going to do 6.3b today. We're going to be talking about the logistic differential equations. So our objectives are that we're going to write and solve logistic differential equations. Whew, that's a lot of words. So what we want to do is go back to pre-calc, where we talked about logistic functions. And we're going to go back and remember that because that was a long time ago. All right, so a logistic function is of this general form. Our calculus book uses the variable L, which is fine. It doesn't matter what they call it, and 1 plus b e to the negative kt. So if you'll remember, A, or L, which our calculus book calls it, is, I'm going to write L, is the carrying capacity, or it is called the limit to growth. And remember, in pre-calc, we talked about in Flagstaff a limit to the population growth could potentially be water, because we don't have a lot of water in Arizona. All right? If you'll remember, it is a very unique graph because it actually has two horizontal asymptotes. It is a growth function. Whoops, and it looks kind of like that, and it crosses there at 1. So there's our handy-dandy graph, and that would be the logistic function. The asymptotes are going to be generated from here, and that would be the limit to growth. All right, the formula does have a constant of variation k, and you usually have to solve for k and b from the data that you're given. All righty, if I talk about this from a calculus standpoint, if I talked about the limit of the function as x approached positive infinity, well, it would just be the carrying capacity of the graph. All right, so what I want to do now is I want to do an example, and I'm just going to bring in what I have already written so that you can see it. Let me get it to where you can see it. Just to make our video a little bit shorter, you can pause if you want to write everything down. So the example that we're going to do says a state game commission releases 40 elk into a game refuge, which is entertaining because we do a lot of elk hunting in Flagstaff. After 5 years, the elk population is 104. Notice this is going to be a data point, so I'm going to have 5 and 104. And then I'm also going to have a data point 0 and 40 because at time is equal to 0, they release 40 into the game refuge. The commission believes that the environment can support no more than 4,000 elk. That's going to be your L, or your limit to growth. And then it says the growth rate is of the elk population is, and notice they've given it to you in a different format, okay? So they've given it to you as a rate, the growth rate of the population with respect to time. And so the first part of the problem is write a model for the elk population in terms of t. And notice our relevant domain is from 40 to 4,000. This is the initial, this is the carrying capacity. Then we want to graph the slope field, which you're going to do in your calculator, okay? And then we're going to use the model to estimate the elk population after 15 years. And then we're going to verify the carrying capacity by finding the limit of the model as t approaches positive infinity. All right, so hopefully you have all that written down. Okay, so pause me and then write it all down. And now I'm going to start doing the problem. So the first part in A, they gave you the rate of the population change, and it is, where'd it go? I have to turn my page back over so I can rewrite it. So it's going to be Kp times 1 minus P over 4, 1, 2, 3. But what I'm actually going to do to start the problem is go back to the equation that we used from pre-calc. So I'm going to write P is equal to 4,000 over 1 plus B e to the negative kt, because I need to solve for B and I need to solve for k. I have two data points. I have 0, 40, and then I have the data point 5 and 104. And we actually did this very problem in pre-calc, not this exact problem, but doing this method. So I have two variables, and I have two sets of data, so I can write two equations. So I'm going to write that 40 is equal to 4123 over 1 plus BE to the negative K times 0. And I'm going to write a second equation, 104 is equal to 4,000 over 1 plus BE to the negative K, and then my X value is 5. Alrighty. Well, if this is 0, then e to the 0 is 1. Okay, so this goes to 1. So I'm going to get 1 plus b is equal to 4,000 divided by 40. Okay, so 400 divided by 4 is just 100. And then b is going to equal 100 minus 1, which is 99. And I'll write it like this. Okay, so there's my first variable that I've solved for. So now what I'm going to do is I'm going to substitute this into here. So I'm going to go ahead and cross multiply as I substitute it in. So 1 plus 99 e to the negative 5k is equal to 4,000 divided by 104. Okay, subtract the 1. 99 e to the negative 5k is equal to, and I'm not going to do this math until the very end, minus 1. And then I'm still trying to solve for k. So a negative 5k natural log e is the natural log of 4,000 over 104 minus 1 divided by 99. Okay, this goes to 1. And so when I do all of that math in my handy-dandy grapher, I get that k is approximately equal to 0.194. Okay, so there's the second piece of information that I was trying to find. But A said to write the model, so now I actually have to write the model. So I'm going to write P is equal to, and I'm going to write model, so I'm identifying my work as I go, 4,123 over 1 plus 99 e to the negative 0.194 times t. So there's my model for the population. The B part I'm actually not going to do because you guys are all brilliant and you have the slope field program in your calculator. So you are going to put this equation into your grapher, and then you're going to use your grapher to generate the slope field. And just as a reminder, your window, your X min is going to be 40 and your X max is going to be 4,000. And then you can do that work on your own because I have utmost confidence in your abilities. Okay. The next part says predict the population in 15 years. Well, that's just easy. I substitute this in over 1 plus 99 e to the negative 0.194 times 15. I push buttons on my calculator, and I round because I can't have a partial ELK because that's just growth. Okay, so then I would say P of 15 is equal to 626. Remember, we identify our work. And then the last one, we're going to do the limit. So the D part says I want to take the limit as t approaches infinity of 4,123 over 1 plus 99 e to the negative 0.194 t. And notice that we actually never used the rate equation that we were given in the beginning of the problem. So we actually found the logistic growth equation, and then we're doing our math with that. So if I look at this particular function, the limit is going to be 4,000 because if you remember, the graph is going to look, here's an asymptote, and then it's going to go, and it's going to look like that, right? Well, we know what it is, but we want to talk about how to do it mathematically. Well, as t goes to infinity, this is going to approach 1. So if I looked at just this particular part of the graph, it's going to approach 1. And you could put this in your calculator and look at the limit that way. You could use your table and look at the limit that way. But as as t increases without bounds, this particular denominator is going to approach 1. Therefore, the limit is 4,000 divided by 1, which is just 4,000. So it was actually pretty easy. Alrighty, that's it for today. I will see you soon.